Okay, yesterday we were having a chat about the way in which to tackle example number 8. You could write out the flexibility equations which we have down here. And as you would note, the flexibility equation is identical to what we had before. So that expression should be identical to this expression here, I suppose, with this just brought to the other side. So when you tackle this problem, all you need to do is to work out the 6, 1, 2, 3, 4, 5, 6. You just have to work out the 6 different values of delta. And then you'll end up with a matrix like we had before when we had 2 degrees of indeterminacy. So you end up with 2 equations, 4 unknowns here. These you've solved here. And then you would be able to, 2 unknowns, x1 and x2. And then that would give you enough information to be able to solve what x1 and x2 are, in the x1 being the force in the first released member and x2 being the force in the second released member. So if you go to the Dropbox and if you looked at FM8, which we've got here, there would be a solution that's been written out in this video here, in this folder here, and then there would also be an accompanying video that goes through how each of these numbers were sorted out, and then that would lead to the final solution of the forces in each of the members. So example 8's there on the Dropbox for you if you wanted to have a look at that. And just remember, it's no different from what we've done before. So we'll have a quick look at the last example in the course book, which would be, so this is the mixed structures where you've got a combination of trusses. And this is example number 9, find the bending moment, shear force and axial force diagram for the king post beam. So with this one here, looking at it, it seems that there's 1 degree of indeterminacy. So I would say it's statically indeterminate by 1. And the best, so that would be the beam section here going down like there. And possibly the best thing to release would be to put your cut here. So we'll put the cut down there, so that would be the release that you've got to put into it. And then you would have maybe two forces down on either side. And then from there, you would just go through the standard calculations that we would do in order to actually find the force acting in the released member using the flexibility method. And again, if you wish to, if you go down here, there's a solution here which you can see with the release down there, and then the matrices, and then one video here, which I guess is the first one, where in this case Puyar goes through the whole work solution. So if you've got any problems with that one, then just please put some messages up on the piazza. So as far as that goes, that basically terminates the end of the flexibility section, and then you can see we've got some examples which you can work through, and I think again you would find that there are solutions for all of these in the Dropbox for you to have a look at. And then previous exam questions covering flexibility, it's always question number 3 in the exam, so that would be question 3, question 3. So in the past exams, question 3. I think the 2016 one was the one where I gave the same question for the slope deflection method, and then you've got to use flexibility to solve the same problem. So, and then this is the one that we went through right at the start. these written by students explaining what the definitions of virtual work, unit load and flexibility method are. And then we come to some of the mind maps that you can see. So this shows you what's covered in EngsGen 121. This shows you what's covered in StructEng 200. And as I think I've mentioned, some practicing engineers, they would basically have a handle on all the different methods: virtual work, flexibility, slope deflection method, and the stuff moment error method, of course, and the methods that you'll be using you'll be learning in the third year as well, and that you would just basically choose the most appropriate method for whatever problem you're trying to solve using hand calculations. So and possible approaches to the problems. If it's static indeterminate, at the moment you've got options between moment area, slope deflection method, and also the flexibility method, which you can see there. And this again would sort of tell you which one is appropriate in different situations. And finally, some exam tips. So some exam tips from the past, and I think whoever wrote this said, the structure of the exam is almost predictable. Yes, it is. There will be guaranteed a slope deflection method question, and then all these guaranteed, and then the critical bit is probably just to do the easy questions first. So when you get to the exam, try and do the slope deflection method problem first. Pick up those marks, and then for the rest of the time, spend it on the other questions. So that brings us to the end of the course book. So here, some other stuff here. So these are the extracts of the previous exam questions. So in the remaining time, I'd like to talk about this question 4 that I've put in as an alternative to the question 3. So to me, it's really just a case of wording, because flexibility and stiffness are mutually interchangeable terms. So what's the lecturer in year 3? So as you know, that they've restructured the course. So before, Gary would be teaching you in the first semester, and he will be covering things extending from this work. He'd be covering something called moment distribution. So Gary would be doing that in the first semester of semester 3, and then in the second semester of year 3, Na'awi Choi, he will be covering some stuff on vibrations, okay? Vibrations, and then earthquakes, and then dynamics. So historically, this would have been a second semester course, and then in the first semester, so we're talking about year 3, first semester, Gary would be talking more about an extension to Struct 200 plus 201. Okay, so my understanding is that Gary will still be doing the course here in the first semester of year 3. So my understanding is that first semester of year 3, Gary will still be doing that, but Na'awi's course has also been changed to first semester. So for this reason, I've introduced a question 4 in the exam, just so that when Na'awi starts to teach you, it's not a major shock. And of course, as we keep on saying, you don't need to do the question 4. in the exam. It's just optional for you, but I'm just making sure that when Awi introduces some terminology, that you're not shocked by what you hear. So the terminology that he would be introducing is this term stiffness. So stiffness is really the inverse of flexibility. So I'll talk a bit about stiffness and actually use the term stiffness, and then you can see that is exactly the same. Stiffness is force divided by displacement. So if, for example, you had two displacements and two forces or whatever, you would end up with a stiffness matrix, as we have seen with a flexibility matrix, and then displacement. So stiffness times displacement is equal to a force. So think of a spring here, and then you've got an object there, and then you put a force onto it. So you've got a force that's been applied here. You've got a force that's been applied here, and then you would say that this spring has a stiffness K. Okay, so K. So you have seen stiffness before. Stiffnesses of a spring, for example. So there would be a K which would be associated with the stiffness of the spring, and the units of that stiffness would be newtons per millimeter or kilonewtons per meter for the spring stiffness. So that's something that you should have. That's something that you would have seen before. So stiffness would not be a new term. So stiffness times displacement would be equal to the force, of course, and displacement would then be equal to the inverse of the stiffness multiplied by the force. So we're talking about vectors and matrices. And what we've said is that flexibility is displacement over force. So the term stiffness and flexibility, stiffness is often given something called K. So K for the spring there. So you would say that the flexibility is equal to 1 over K. Okay, so the terms are exactly the same, just one is the inverse of the other, which is why I said if you understand flexibility, then stiffness is not really a big deal. So what's the stiffness of a structure? So just stress again that all of this is optional. So if we say here's a structure, okay, here is a structure, and then there is a force P, P being applied, and it says determine the stiffness, determination of the stiffness K. So we could say determination of the stiffness, determination of the stiffness. So what is the stiffness of this? And you could sort of say, you could relate this structure here to the effect of all of this onto maybe a force being applied there. So that could have a spring stiffness, and whatever that stiffness is would come from the whole structure there. Okay, so it says what is the stiffness what determination of the stiffness, and that basically means what is the displacement under the load P. So there would be a displacement under the load P, which we can calculate, and then we would then say that stiffness of this spring is just basically going to be equal to the stiffness is basically going to be equal to P over delta. Okay. Hello, I'm trying to record the lecture and I don't have the pause button. I'll get it. I'll come upstairs. Right, so hopefully what I've said should make it very easy for you to know what to do. So we basically just have to calculate the deflection. So instead of saying what's the flexibility, we'll be saying what's the stiffness, and to get that we get the deflection, and then P over the deflection would give you the stiffness. So when Na'awi says what is the stiffness of this structure, what he means is calculate the deflection, P over the deflection would give you the stiffness. So if you want to calculate that deflection, first thing to do would of course be to draw the bending moment diagram. Sorry, I don't have any locks on my door. So the first thing to do would be to draw the bending moment diagram of the real structure here, which would be like that. So draw the bending moment. So you've got the real structure, and then you've got the virtual structure here. So we want to calculate that deflection there. So we would just stick on the one. So this would be the virtual one on this side here. And then you've got your two bending moment diagrams, and then from there we would get the deflection. So using 1 times that one there, so one times that one there would be equal to the integral of the real bending moment diagram multiplied by the virtual bending moment diagram, 1 over EI, and then you'll do that from 0 to L or whatever it is, and then you do that over dx, and of course that's going to work out to be 2 times this portion here, times PL times L over 2 times 2 over 3L, and divide that by EI, and we will get 2 over 3 PL cubed over EI. Okay. So when we say what is the stiffness of the structure, so this hopefully is a very simple sum for you to do. We're basically saying put that into the equation. So you've got your deflection, which is going to be 2 over 3 PL cubed over EI, and then that one is going to be 3 EI over 2L cubed. So this, to get the stiffness of that structure is hopefully quite a trivial task. Okay, so now the second problem which Na'awi has talked about, in that he's asked you to be familiar in year 3 to be able to do, is this one here, and then we've got P acting down there, and then determination of the stiffness K. So to determine the stiffness K of this structure here, okay, so we want to work out the stiffness of this structure here. So we've got the unit load method, and of course there's going to be no bending moment here. So when we take that one there, and then we stick the virtual force there for the bending moment diagram, and then you get the bending moment diagram of this one here. Then of course to get the delta would be using the unit load method would be 1 1 times that is equal to the integral of m bar over EI, and then that would end up as being delta, so that would end up as being delta is PL cubed over 48 EI. Please don't expect a question as simple as this one in the exam. And then for the optional question 4, which can be done instead of the other question, and that's equal to 48 EI over PL cubed. Okay, so that's the second one, and this one would be the stiffness, i.e. you could take that and then put the force P, and then the stiffness of the spring there holding P would be given by that expression. And if you wanted to know the flexibility, then the flexibility is just the inverse of the stiffness, as we've been saying all along. So there's now a more complicated one to talk about. So the more complicated one would be this one here. So we've got that there, and then we've got that there. Okay, so this one we would say is rigid, and then this one here is going to have a force P there, so now you can see that the left hand side is going to be anchored by a bar. So which would have an axial stiffness of EA, or you could say a spring stiffness. So this would be a rigid frame, and then that one would be something like going there into here. So in terms of the frame members, we're saying that is the frame member here. So that is the frame member, and this bit coming down, and then on top of that we've got something coming like that, and something else coming down there to the ground there. So the question could be work out the stiffness of this structure, which basically is you've got your force P, and you've got to work out what the deflection of this structure is under the force P. So of course you can do it using the flexibility method, but the point here is that sometimes the stiffness method or the stiffness approach may be a faster approach than the flexibility. So of course you can use any of the methods that we've described in the course, or even before the course, but it's choosing the most appropriate one. So for this one here, it might be most appropriate to be using the stiffness method. So you've actually covered everything that you need to be able to do this already, but I'll just draw your attention, if I may, to so when we have a look at the appendices, and I'm looking for the fixed and moment charts, which hopefully I can find. So we've got you've got the special cases, and then you've also got the general cases down here, which you can see there.